First one, sampling theory is easy. So we are consider first issue we are talking about the scalar quantization. So scalar quantization is meaning we are trying to reduce the data. So reduce the data. If you are quantize, so you will be reduce the data. So quantization is look like a volume reduced, and then you have some label. So quantization, we have a called quantization level. One is called quantization level, is more like a level, is more like a representative. So it's more like a representative. So we try to find small amount representative to represent your original more diverse to present. You try to using small amount representative value and to present more diverse original data. So you can see we are trying to more diverse original data. So it looks like we make some data loss. So quantization indicate we have loss. So how to make a good quantization? Scalar, first one we call the scalar quantization, and also we have vector quantization. We also have a vector quantization. One is a scalar quantization, the other is a vector quantization. So scalar quantization is based on one component by one component, is component based, just one value. And vector quantization indicate your quantization component is based on vector. Minima, they have each vector have two elements or more depend on your application. So quantization, first one, we try to find better quantization level. That quantization level try to indicate you have some representative, using small amount representative to indicate more complicated data set. So according to this idea, so we try to, because in this course we are talking about compression, try to make a good use, reduce your data volume. So critical scheme is quantization. So you can see our this table, this figure here. So we have a quantization. So you can see this this presentation file here is more like a scalar quantization. So we have an input and we also have an output. Our input is S1, S2, S3, S4 up to S5 and S6 and 7. So indicate you have many data. They are continuous mode. So your data could be big. S4 could be 0, S5 could be like a 1. You have a value between 0 and 1. You'll be using Wi-Fi to represent the data. So it looks like your continuous mode will become a discrete mode. So here they have a 8 level. So Y1, Y2, Y3, Y4 up to YA is your representative vector. So we have 8 level. So you can see here 0, 0, 0, 0, 1 is more like an index. We call quantization level, and then they are encoding bit. This one is our encoding bit. Encoding bit is look like 0, 0, 0 or 0, 0, 1. But this one is not a value. It's try to encoding how many number you have quantization level. So like this example, we have like this transparency, we have total 8 level here. So you can see we have a level. So encoding bit using 3 bit. However, each bit is more like a memory addressing or memory index. However, the content can be one specific value. So encoding bit is not equal quantization value. So you have to understand one critical part, quantization. So you have a quantization encoding bit. Encoding bit is not equal to your quantization level. What's your quantization level value? So it's not equal. However, some application like an ADC converter, analog to digital converter, so maybe like an AB converter. So they try to encoding bit. The encoding bit could be maybe equal the value, but most of application quantization encoding bit could be not same as quantization level value. So here, for example, we have like a one example. So maybe we have like a pixel, image pixel. So suppose be pixel grade level, like a grade level, we define 0 to 255. So each pixel will be using a bit to coding. However, if we try to quantize them, we are assume we only using 3 bit to do it. So if we are using 3 bit to do it, so we only have a quantization level. So a quantization level. So you have a 2 power a divided by 2 power 3. So the quantization step is 32. So this one we call quantization step. We call this one is quantization step. So you can see here, if the value if value 0 to 31, our represented quantization level will be using 15 to represent it. And then 31 to 63 will be 8 by 16, so you'll be 47. So you'll be 8 by 32 will be 47. So your representative will be 47. So 0 to 31, I will be using 15. 31, your grade level from 31 to 63, I will be use 47 to represent the data, and so on. So you can see the last one will be 255 minus 32 minus 31 is around 2 thirds. So around 2 thirds and 255, I will be using plus 16. So you'll be using this one will be using 239. 239 represent, if you are grade level between 223 and 255.11. However, this one is like an index quantization encoding bit, but in reality, the represented value is 15. 000 is 15. 001 is 47. 111 is 239. So from this application, so you have to be distinguishing what's the quantization. One quantization, we try to find better, the best one, the optimal one is quantization level. But the quantization level, we have to encode it. So how to encode quantization level depend on how many you have quantization level. In this example, we have a quantization level. So each quantization level, because we only have a level here, so we just using 3 bit is enough to address it. But each quantization level is not a 0, 0. 15 is not equal to 0, 0. 0, 0 is addressing. So you have to be distinguished. What's the difference between them? So later on in last week, we talking about we try to define the quantization error, and then also we are develop the quantization error here. So here they are assume signal between these two level, between this area. So you can calculate if you are signal coming signal S of n, Si is your quantization level representative. So delta I is more like a step size here. So you can see here. So delta is step size here. So you can see delta is step size here, and S of n is your original data. So Si minus delta I. So if you are input signal between this bottom, this upper bound, this lower bound, upper bound and lower bound, signal between these two range, your S of n is represented by S of I. So for this range, so if we are calculate the distortion, so we can input data minus your represented quantization level, and also consider each data appear probability we call P of S. So we are trying to integrate their distortion, so you can calculate mean square error around this kind of range. So this for this specific quantization level, and for EI. So we have many EI, so you'll be summation then and become the total mean square error. So according to this equation, they try to recalculate and become the equation that one for each quantization level. They assume your probability density function is uniform. So the P of Si can be put out from your equation, put out your integral symbol there, and then we do the integration here, and then we get the equation like this one, and then we try to calculate the probability. If we are trying to calculate the probability, because this one is for one specific S of I probability density function, and multiply the step size. This step size indicate if you are this region symbol input signal below using SI for representative. What's the total probability portion? What's the portion occupy whole data? So this one is for one individual probability density function multiplied by their region, step size region. So you can see here, so they can know the probability of signal falling in the ith interval. So we can using the last two function, we combine them together, and then we are remove P of Si, because we have this equation, we have this EI square, and then we have a tau I. So we try to remove P of Si. So you can see we can derive EI and tau I relationship here, and total mean square error will be come out because our quantization level, we assume we have an n quantization level. So we have an n quantization representative level. So we try to summation them together because this one just for one quantization level. One quantization level, what's the error contribution, and this one is many quantization level, what's the total distortion. So for this example here, you can see our because we have a quantization level, this one is grade level from 0 to 255, so we have a quantization level. So each quantization level, because 0 to 31 will be using 15 to represent the data. So if your pixel is 0, so because you're using 15 to represent the grade level 0, the distortion will be 15. So like this example, they calculate this quantization level mean square error, and also 31 to 63, they also calculate, they are using 47 to represent it. So they also calculate quantization error here. So that there will be summation for each quantization level. They contribute distortion. What's the total distortion? There will be summation then together. So you can see if we calculate the total according your quantization level, so they do the summation, so they can see they will be related to your step size square divided by 12. But however here, the assumption your uniform quantization, so the step size will be equal. Like this example, you can see our step size is 32. So each quantization level, they have a deviation. They have a difference, but around the 32. So they are uniform quantizer. So they are uniform quantizer. So they move in the front. However, tau I is indicate your probability. Each quantization level contribute your probability. So suppose we hold the probability, whole quantization level occupy your data dynamic range should be equal to 1. So this summation will be equal to 1. So you can calculate if your quantizer, scalar quantizer is uniform quantizer, so your error function, you can get delta square divided by 12. So another one is a uniform quantizer. So uniform quantizer here, because in the past we are consider your dynamic range is S 2x maxima. So right now we are consider how to assign the bit here. So you can see our dynamic range is 2s maxima. So they indicate because this one is scalar, so your input data dynamic range is minus s maxima and s maxima. So your total dynamic range like this one, and then your quantization level is delta. So and then how many you have? So the number of quantization level you will be 2 and b. So depend, because if you are b is encoding bit, 2 power encoding bit is indicate you make a good use your encoding bit to represent your quantization level. So this one delta is quantization step size. So quantization step size multiply your quantization level, number of quantization level equal to your dynamic range, So you can get it like this equation here. So here you can see, here you can derive equation by 2x maxima divided by 2b. So you can see your uniform step size will be equal to your dynamic range, input data dynamic range divided by your encoding bit. So in 2 power your encoding bit. So uniform quantizer, we another one, we try to calculate signal to noise ratio. So our input data, you can see our input data will take a square, and then each input data we counted their probability density function. So they have dynamic range is S minus maxima to X maxima. So we can do the integration there. So we can get S maxima square divided by 3. So this one is our power more like a signal power, and Pn is more like a noise power. So it's more like what we calculate noise. What we get here, we calculate the noise here. So this is our signal power, and this one is our noise power, and then we divide by then, so we can get the signal to noise ratio is related to power to B. So if we take the log scale, because this one is energy ratio, so we're using 10 log 10. If this one is amplitude ratio, we have to take 20 log 10. So here this one is energy here, energy ratio, signal energy rate versus noise power, and then will be take 10 log 10. So it will be 2 power to B. So we can calculate around 6.02 dB. So you have to remember this one. If your quantizer is a uniform quantizer, and then your signal is a uniform distribution. So if your signal is a uniform distribution, so your signal is a uniform distribution probability density function. So your data is a uniform distribution around your dynamic range. So this S maxima. So this one is your S maxima. So each data is uniform. So this one probability density function will be 2S maxima. So, and then also your quantization step size is the same, delta 1 and delta 2 and delta 3, they are all the equal. So the quantization step size, they are all the equal. So we are called a uniform quantizer, and signal is a uniform distribution, probability density function is a uniform distribution. So based on this kind of condition, so if we are encoding bit increase 1 bit, indicate your quantization level double. So if we are using 3 bit to encoding, so indicate we have a quantization level. So it looks like a 2 power 3. If you were using 4 bit to encoding, so your maximum quantization level is 2 power 4 is 16 quantization level. So in here you have to remember if you are using more bit to do the quantization, and then more bit to do the quantization, indicate you have a more quantization level to quantize the data. So such as under approach, so you can under such approach, so you can make your noise reduction, reduce your noise, reduce your loss, reduce your distortion. So you can see if we increase one bit, you can increase the 6 dB. For example, like an AD converter. So if we have an AD converter, like an A bit AD converter, if you have an A bit ADC converter, so signal to noise ratio, so there will be A divided 6.02, so it will be 48.16 dB. If we are using 16-bit ADC, so your signal to noise ratio will be double again, will be 96.32 dB. So you can see if we are using a more high bit ADC, if we are increase 1 bit, supposedly you'll be increase 6 dB. So the reason is come from previous what we did derivation. Okay, I using the Mandarin a little bit repeat again. Okay, 量化有分成Scalar 就是一个就单一元素的量化，跟向量量化。向量量化通常最少要有2个元素。那量化你一定要分清楚 量化的 level， 也就是代表值，还有你的量化的数目，就代表说我要给它的编码的长度。如果我量化 level 只有8个量化 level 只有8个，每一个 level 我只要用3个 bit 就可以了。那但是呢，每个 level 可能表示的值不一样。好，就好比说前面我给的例子，你的影像的灰阶度是0到255，然后但是呢，我如果用8个 level 去量化，所以说呢，8个 level 量化呢，我每一个 level 只要用3个 bit 000，但是呢，我不可能8个 level 用000表示0，001表示1去量化0到31，31到63，这个误差就很大。原则上0到31我的量化的值是15，31到62我的量化值是47，但是它的编码是001。好，所以说编的码是跟你量化的代表值的数目有关。好，那编码的长度是根据你的量化的数目。好，那我们刚才在推的那个式子，也就是上礼拜讲的推的式子，实际上在做，因为我今天不再推了，是上礼拜推过了。好，如果不懂的学生，可能将来你可能要送个信给我，可能怎么去跟你在当面再教，线上再教你，直接针对你的问题做教导。那原则上我的讯号假设你的讯号是在这个区间内，你实际上你这是原始讯号，你实际上是用 SI 来代表，在这个动态范围内。那如果你的讯号在这个范围内 S， 好，它这个符号用的不好，接下来它用的是 S， 那在这个范围内都用 SI， 那但是呢，我们误差呢会根据你的 S 出现的几率有关。比如说我不常出现，你算这个误差没有意义，所以说我通常是要看每个讯号在这个区间出现的几率，在这边的几率呢是假设 uniform， 也就是说每个值出现的几率大家都一样。好，那所以说它会把 P of 3拿出去，那前面的式子做一个转换，你就会算出这个。那这个东西呢，实际上就是每一个点在这个区间，我的每一点的几率算出来的时候，这个算出来是代表什么意思？算出来用 quantization level SI 来表示，然后假设它是 uniform， 所以说 uniform 大家在这个区间每一个点的几率都一样，所以说 PSI 是会拿出去，然后呢就乘上它的区间的什么间隔的大小。就好比说我刚才举的这个例子 uniform quantizer， 那你的动态范围是负 S maxima 到 X maxima， 你的 probability density function 是2，那平均的几率呢，就是每一个点平均就是2的 S maxima。那这个区间我用的是某一个 SI 来量化，实际上就是这个的每一个点乘上它的 delta， 就是代表这个区间所占的大小。好，那有了这个时候，你就可以算出你的每一个量化 level 的误差，乘上它这个 delta 占的这个区间。那接下来你所有量化 level，假设有 n 个量化 level， 你就会加总。那这个是 total 你的 error， 就跟你假设你的每一个量化的阶梯，量化的间距都一样，所以 delta I 就拿出去了，就变成这样。那接下来你会算我的动态范围。跟我是一个 uniform quantizer， 量化间距都一样。那原则上我为了善用 bit， 我是用 b 个 bit， 假设我用3个 bit， 我的量化 level 就最多就是8个。我是4个 bit， 我最多量化 level 16个。你说可以少一点吗？15个吗 ？OK， 但是你没有善用你的 encoding bit。好，原则上我们要善用2x maxima 除以 2b 就等于你的 delta uniform quantizer。那你可以算出你的讯号的 power。那讯号 power 除上你刚才算量化的失真的 distortion， 就是讯噪比。那接下来你就会发现，你讯噪比就跟你的编码的位元有关。你给的倍数越多，你的讯号的表现就好，讯噪比就高。所以说你可以发觉每增加一个 bit， 你可以增加6 dB。那 AD converter 16 bit 就是大概96 dB， 8 bit 只有48 dB。所以说大概因为 AD converter 我们都假设是自然界的任何讯号，它的动态范围都是 uniform 的分布的话， 那原则上我可以假设你的 AD converter 的转换是一个线性，而不会是非线性的现象，那这时候你的 performance 应该可以达到这么好。Get a better optimal quantizer. So last time I told you if we know the probability, your probability density function, if you are input data, we know your probability density function. So this one could be not good. So if you have probability density function like this one, so we can consider most frequently. So most frequently, this region is a high frequency come out data high frequency data. So high frequency occurring. So boundary signal is a low frequency, is not a high frequently. So we can say high frequently occurring. So this one is a low frequently, is frequently occurring. So 常出现一个不常出现. So if this one probability dynamic range, the probability is higher, indicate this region data come out more frequently, more often. So if we are come out more often, so our quantization level in here, we have to give them more depth. So more data quantization level in here. However, here quantization is not come out frequently, so we can use a more bigger region. The step size, this one step size, and this one step size. So you can see step size delta 1 bigger than delta 2, because this region signal come out more frequently. This region signal come out is not so frequently, low frequently. So we can consider in this region using more quantization level to quantize, make a data loss lower. So you can see like this one is some kind consider your signal probability density function. So you will be consider your signal what's the behavior, come out the behavior. However, you have to know in advance. Otherwise, you cannot design the quantizer. So you can see this example here, the transparency here. So they are not equal. So you can see Y5, Y4, Y6, and Y8. So their step size not equal. So Y4 and Y5 will be closely, and Y2 and Y1 have a bigger step size. So it looks like our data will be more frequently come out between S3 and S5, S6. In this region, we're using small step size. And the other region, they come out not so frequently, not often come out. So we can use in bigger step size. So the main idea here, we try to make sure, if you know the probability density function, it is very simple. You try to partition, if you are quantization level, using another one. So if you know you have an input data, you have a probability density function. So if you have an input data here, so for example, we are quantization A level. So we try to partition A level. So you can see here, and then in here will be more closely, and later on will be more diversely. And then, so 1, 2, 3, 4, 5, 6, 7, 8. So you can see we try to make sure this region, delta 1, delta 2, delta 3, and delta 4, and delta 6, delta 7, delta 8. Oh, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, oh, I forgot 4. 4, 5, 6, 7, delta 8. Okay, so you can see more frequently this region, the data come out frequently. So this region, the data not frequently coming out, you know. So it's not frequently coming out. So the optimal solution is try to make sure you integrate the area, this area. We try to do the integration. So we try to do the integration between your step size delta 4 and try to do the integration this area. So we have an A region. We try to do the area integration. Make them the equal. So according each region, we try to find the centroid point. This point will be each region. We find the centroid point, and then that point will be your representative value. So it will be your quantization level. So that one is your optimal quantization level. So you can see like this region. So quantization level will be close centroid 重心点. Centroid will be close like left hand side. So like this one, you can get the optimal quantizer. However, under this assumption, you should know your probability density function. Maybe some application is not available. So this transparency maybe show you one example in textbook, but however, in textbook they did not give more detail. They just show you one example here. They do the quantization level using different bit. Okay, another one we are consider. Okay, so in the beginning, sorry. So we this transparency show you we have a logarithmic quantizer. So in speech processing, we have North American standard and Europe standard. So one we call the A row, the other we call the mu row. So the original signal, speech signal. So our original signal, like your ADC signal. So try to recoding signal from the natural world. So more like you have a microphone. They have a membrane of vibration and trigger your electronic circuit and generate the analog signal, and later on analog signal will be due to the ADC converter become the signal. But this signal is original signal. So original signal. So later on we have to generate the PCN. PCN is more like a A row and B row. We have A row and mu row. One is American standard, the other is North American standard, the other is European standard. So according their equation, more like they try to if you are signal dynamic, this one is your input, this one is your output here. So original dynamic range is more like supposed to be linear, will be like this one, but this one could be in the beginning is linear, and later on will be more log scale. It's more like a log scale. So your input data become the bigger. So our after error and mural, so there will be signal will be a little bit like log scale, So this one is similar. It could be similar to the human perception. Is considered human perception. So human perception is not a microphone sensor. It's not like a microphone sensor behavior. So we are do a little bit like a log scale. Try to make sure your signal, the amplitude is a little bit similar like a human ear perception. Okay, so this one we call the error and mural come out. Okay, I try to repeat previous one. I forgot using the Mandarin. So optima quantizer 那个最佳的量化，实际上如果你已经知道你的输入的讯号的几率函数，也就是说它出现的那个叫做几率密度函数。那 probability density function， 也就是说我的 input 是1，我出现的几率占多少？2，我 1.1、1.2， 当然是连续的。那出现的几率到底多少？如果你知道你的 input 的 data 的特性，那前面刚才推的公式呢的 probability density function 是一个 uniform， 是一条线，类似像 DC。但是呢，自然界很多的应用并不是像 DC 一条线。它可能是一个像这个我举的像有点像高斯，那所以说在几率出现高的地方，我会用比较多的 quantization level， 也就是它的 step size 会短。那不常出现的，我会让它 step size 大，那也就是说它用的量化的 level 就会少。那整体来看，失真会变小，因为我们需要让整体失真变小。也就是说你密集出现的区域，我给你较多的代表点，让你那个密集出现的失真呢不要那么多，然后不常出现的我就用的代表点就少。那因为我整体的可以编码的量化的 level 就固定了，那所以说我就可以根据你的出现的几率来做给定。好，这个是它的基本精神。OK， log scale. Okay. Another one, because we are not well know your probability density function in advance, we can consider another way we call the adaptive quantizer. So adaptive quantizer is based on currently what kind of data type you have. So right now your data type, we can dynamic to update your quantization level. So for this example, we are consider your input signal. So from the transparency, our presentation file here, you can see our signal energy. We are consider try to summation your previous signal. We are trying to calculate your dynamic mean. So here you can see our input data come in, and then we have a buffer. We try to look at many data in the past, and then we estimate your dynamic range, and then we give them your here you call maybe your standard deviation. So we know your deviation, and then however this standard deviation, we have to you have to be, if you are design encoder and decoder, they have to be synchronized, because if you are change your quantization level, some mechanism to do the adaptive, you have to be inform your decoder to know how to do the adaptive. So you can see your input data, we calculate the deviation, and then we quantize your deviation, standard deviation, and then we using the quantized deviation sent to decoder, and then using this one deviation, and then they also do the quantize. So they do the quantize your standard deviation. So send out is index encoding bit. Encoding bit is not a quantize. So this send out is in index, and then this quantized value will be come out to do the divided, and then make your signal. So suppose your signal dynamic range original so big, divided and make your signal dynamic range become the smaller, and then we can design a quantizer. Quantizer is more like a uniform unit. We call it unit quantizer, unity gain quantizer. So unity gain quantizer, because we are consider the gain between a -1 and 1, so we can, it's not a focus any dynamic range, because we already estimate your dynamic range, and then we are do the scaling, make your dynamic range become the -1 and 1. So our quantizer, we can design unity gain quantizer. So later on, you'll be saying index is more like an encoding bit your signal. Okay, it's not the original quantized data here. So and decoder they will be get is index is more like a encoding bit here, more like we call them like an address. And then this one, the quantizing is more like a table lookup. The quantization is more like a table lookup, So table lookup is, this one could be the addressing. So you can, the quantization, you can recover the data, recover here, and then another one you get index here. Index here is standard deviation, is more deviation index. Here they also look like the quantize. So this one you also have table lookup, the quantize. So the quantize, so they try to multiply here. So they try to reverse this before they do the division. Right now they do the multiplication, and then you can recover your signal back here. So this figure maybe is not clear, you will be confused. Quantized value did not go through the channel. We only send encoding bit, so it's indexed to indicate your quantization value. So however, here you can see our input data, we have a quantized index value. However, we have additional index to indicate your quantization index. So this approach we call the forward adaptive. Why we call it a forward adaptive? Because supposed to be our original, we talking about the quantization. We try to think about how to design the best quantizer. What's the best quantizer here? And later on, we are consider some adaptive mechanism. So before you do the quantize, we try to try to adjust your data, and then you have to talk to you have to talk to decoder how to adjust your input data. So this one is additional information. In the previous presentation file Slider, we did not say we have to do the adaptive. We just say how to design a good quantizer based on your input data, probability density function. Here we consider adaptive. So we are consider your input dynamic range, and then we are scaling your input data become the unit gain. So we can design unity gain quantizer and go through channel. We not only quantize data index, we also we also have additional overhead. Try to tell the decoder how to adapt your quantizer. So this one we call the forward adaptive. Okay. Another one we call the backward adaptive. So backward adaptive is now you can see the figure here. So our input signal will come in will be to the we are using your previous. So first one we are trying to quantize. So we quantize the data, become the data. So this data supposed to be we have to dequantize back. So this one is index your SN help your SN. So we dequantize back, get the data. So this data will be do the estimate. So we have to be using this one, dequantize. So we estimate. So your standard, your deviation, your signal dynamic range. We try to know what's your dynamic range change. So here you can see here we have to go back to multiply. So here is more like a decoder. You can see this one is similar, like we have another decoder here. So this one supposed to be, this one is encoder. It look like an encoder including the decoder. Why? Because we do not like send additional overhead. We only tell the decoder, this encoder, we are trying to using your decoding information. We are using your decoding information. Decoding information could be you have a buffer here. So you have a buffer here. We try to using your encoding information. Encoding information, try to estimate how to quantize, how to scaling, how to do the scaling, the next input data. So we are based on previous your dequantized data, try to estimate your dynamic range change. So this one we, because we do not have a additional like a additional overhead to inform the decoder how to do the adaptive. Our adaptive is based on our decoding signal. So like if we are decoding signal, you find out, well, our decoding signal closely become bigger. So decoding signal become bigger. So our scaling, this one decoding signal, and then we have like a scaling factor. We call this one is scaling factor. We estimate though. So you can pass on, well, our decoding signal become bigger, so our scaling signal supposed to be will be become bigger, and then our decoding signal become smaller, so our scaling factor will be come down, go smaller. However, this one, their response signal, so their response to the signal, of variation will be slower than the previous one. Why? Previous forward adaptive quantization, because previous one we are based on current, your input signal, and then we can do the estimate first. Like current, our input data suddenly become bigger. So our current input data suddenly because smaller to suddenly becomes bigger. So we can base on current input data to do the estimate. However, this one, backward adaptive, we are based on previous decoded signal. So maybe could be related to next one, but it is not real time to response current variation. So suppose be your backward adaptive, there's no overhead encoding bit, but the response, the signal variation could be slower than forward adaptive, but they have a good performance. There could be have a no encoding bit rate. There's no additional overhead. Okay, so you have to be know what's the forward adaptive and backward adaptive. So you have to know forward adaptive. So forward adaptive, you have overhead to sending your additional index, additional encoding bit to indicate how to adapt it, how to do adaptation. So backward adaptive, there's no overhead, but the performance is better than backward adaptive. Okay, so this one is adaptive quantizer. So another one, so the first adaptive quantizer, we are based on signal dynamic range. So we estimate their more like a deviation, standard deviation, using their standard deviation divided by back original signal, become their signal variation become unity gain. So we can design unity gain quantizer. Okay, another one they call the one-word quantizer. So adaptive quantizer, another one, we can select different scaling factor according decoder signal to select the best one. So this one we have suppose be we have the buffer. This one we have the buffer. To do the try to remember decoding signal. According decoding signal, we estimate their deviation to do the scaling next signal. However, this transparency they show you, we pass on decoded signal. So you have S of n. So they also try to do the unity gain, but they only use. So this one you have a quantizer, and then this one you are using send out the encoding index. You are S of n. So supposed to be you have a dequantizer. Using dequantizer. Oh, I don't think so. So could be you can using the addressing to select the best scalar. Select what kind of quantization. Maybe you can, because your index, so assume your index bigger value indicate a big index larger could be indicate larger value. Small index could be indicate small value of your quantization level. So you can using the index to select which one to do the scaling. So you can also use in this one. So they call the one-word memory. So this one Previous one, you are decoding, they consider many previous decoding value to calculate your standard deviation. Standard deviation should be considered among a small amount of data to estimate their amplitude dynamic range. But this one is consider current decoding index. A coding index will be try to select the select some proper one. I assume your small index indicates small quantization level. Higher index indicate higher quantization level. So we can, according your index behavior, to select the proper quantization scaling factor. So this one scaling factor maybe is not proportional related to original signal. It's not, but proportional, sometimes proportional. So they call this one is a one-word memory. This one will be considered many word to do the adaptive. This one just consider one word. Previous decoded data to select the best one, maybe proper one to do the quantization, to do the scaling. So for large quantized previous sample, so multiply value are greater than 1 or for smaller. So this one just show you some example here. So it's not okay. Another one we call the differential quantizer. Why we call the differential quantizer? The big idea is neighboring signal, they have some correlation. So we try to make sure our neighboring signal, because quantization, the data, so you can see we are trying to scaling your data. So we are scaling data. Supposed to be like previous one, bigger dynamic range become a small dynamic range. So can make a good use of your quantizer. So if we have like our input data, our speech signal, so our speech signal is more like this one. So if we are trying to using S of n divided by your S of n minus 1, I assume you take a differential. So because your neighboring signal, they are very close. So your signal will become like this one. So your signal dynamic range will become smaller. So we can make a good use quantization. Your distortion will become lows. So for example, if this one we have using a quantization level. So you have a bigger dynamic range. So you will be make your loss larger. If we are trying to pre-processing, your signal do the pre-processing. So you can make your signal dynamic range become smaller. If we are only using a quantization level, so the signal distortion could be lower. So supposed to be differential quantizer. So if we design a differential quantizer, the main idea, so your neighboring signal have a high correlation. So we try to do the subtraction first, neighboring subtraction first, make your correlation become lower. Look like they have a signal, they have a DC term. We divide by their DC term, make only deviation. Sometimes make your quantization performance better. Okay, so I using the Mandarin. Briefly repeat previous one because differential quantizer I have to talk in next lecture. OK， 上个议题就是说，实际上 最佳量化我们讲过，根据 probability density function， 那人耳听觉不是跟麦克风的感测器一样？那所以说，在讯号 AD converter 进来之前 ，ADC 进来之前，它会把原来的信号做 log scale 做成 log scale 的，不是麦克风的 membrane 的感应，它会经过 ADC。把原来的讯号经过 error mirror 变成 PCM 比较讯号小的接近线性，讯号大的慢慢是 log， 那比较接近人耳error 是北美的规格 mirror 是欧洲规格那不同国家为什么会定义不同规格？实际上当然有专利政治的因素或是标准的因素那都有利益的关系然后 adaptive quantizer 的意思是说，我如果我能 encoding 的 bit 就是3个 bit 或是4个 bit， 那我又不能事先知道所有信号的特性，那我能不能及时的去估算现在讯号的特性，利用现在讯号的特性来做量化那这样的话可以让我的量化的那个效能变好，失真变少。那第一个例子他举的就是把原来的讯号动态范围从大的动态范围变小的动态范围。那实际上它的好处就是我只要把原来的讯号做什么？做评估它的standard deviation把它的那个 deviation 除掉，那就 index 还原量化的讯号，有失真的讯号。所以说你会有额外的 overhead， 那这种的 overhead 会有 overhead， 我称为 forward adaptive， 那它需要额外的 encoding bit， 但是效果当然会好，因为你付较多的成本。那 backward adaptive 呢，当然就是不做 forward， 不做这些事了backward adaptive 实际上就是某种程度用 decoder 的讯号去做处理那实际上是用 decoder 的讯号实际上 backward adaptive 是用 decoder 的讯号去做处理，大概是这样。那 backward adaptive 当然是比较反应没办法及时反应input 讯号，那但是它没有 overhead 送额外的 bit。那课本这边写的都有点错，它实际上是不是送量化的值，是送量化的什么index， 它的那个 encoding 编码，那个编码到 decoder 呢，它的 dequantize 就有点像 table lookup addressing， 按照编码把原来讯号还原那我们 source coding 呢最重要 encoder 会比较复杂， decoding 呢通常会比较简单adaptive 你一定要记得什么是 forward adaptive， 什么是 backward adaptive adaptive 就是说我要善用我的量化，我可不可以根据讯号的特性来分析讯号的特性，来做一个某种程度的处理，让我的这主要的量化器能有效的发挥效用，让它失真减少。那另外一个刚才是考虑一组 data 有 buffer，那这个是不考虑，就直接利用假设我的量化 index 比较小的，就是代表比较小的值大了那根据我量化后的 index 去选我将来可能要来做 scaling， 所以我不直接看不直接去分析还原的讯号，也不直接看原始讯号，直接根据你可能的 index 偏大了或 index 偏小了，选一个相对应的除 Scalar 这个就 memory 就减少了。那其次的话就是 differential quantizer 之所以能用，是因为我的语音讯号、相邻讯号有相当高的 correlation，那我可以先把它相邻的讯号，两相邻讯号如果做相减，它的动态范围就会变少，我就可以针对较小的动态范围设计善用它的 quantization level， 让它的失真变小。Okay, our first section, we stop here and take a 15 minutes break. I will be talk to you later. 15 minutes later. Okay, that's it.